Hi, so today we're going to talk a little bit about electric circuits. Some things you already should have done before viewing this video. You should have looked at the discussion and answered the discussion question about electrical safety in your home and what electrical safety practices you have. And then you should have done the circuit inquiry lab, the little simulation online where you built some circuits in different configurations. And once you've done those two things, then you'll be ready for this video today. So the first thing I want to ask is for you to think about in that simulation when the bulbs changed brightness. So what kinds of things do you think made the bulbs brighter? What kinds of things do you think made the bulbs dimmer? And what actually is happening in a circuit to cause that? So you might be thinking, oh yeah, we just added another battery to our circuit and that made the bulb brighter. Well, yes, but what is that battery actually doing? Keep that in mind. Try to come up with an explanation for that as we're talking today. So in the circuit, we're going to look at how to diagram a circuit in a little bit. You should have viewed that video in your simulation activity you did. But I have a question. Which way are these dots moving? So look at it for a minute. Now, I didn't tell you which color dots. So electric current is a really interesting thing. If you follow these red dots, the red dots appear that they're moving counterclockwise. So those would represent our electrons in our circuit. Electrons will flow around from the negative terminal of the battery around to the positive terminal of the battery. But before we knew electrons were even a thing, we were using electricity. And we accidentally labeled electric current the wrong way. So if you look at the white dots, which represent like the spaces in between the electrons, where there's not really anything there, those white dots appear to be moving clockwise in this diagram. So that's the direction that we originally labeled electric current. So you might come across some vocabulary that says conventional current. Conventional current flows away from the positive terminal of the battery and around to the negative, but our electrons actually go from the negative to the positive. So it does get kind of confusing. Actual conventional current flows positive to negative, even though there's nothing actually flowing that way. So let's talk about like what this current is. So electric current, the symbol for that is a capital I. Think like intensity. Current is the flow of electric charge through a circuit. So if you have more current, your light's going to be brighter. You're going to have a more intense light. The units for electric current, we call them amperes or sometimes amps. You'll see a capital A to measure that. And current is, since it's the flow of electrons, it's the same everywhere in the circuit if that circuit is one single loop, if it's a simple circuit. So the current, the rate of flow of these charges is going to be the same at every point along this circuit, at every point within the same wire. Then we have voltage. Voltage is the thing that pushes that current around. You can think of it that way. It's also voltage difference or voltage is also called potential difference. We won't get into the nitty-gritty between voltage and voltage difference for us. Let's just call voltage potential difference. It's going to be all the same for us. So potential difference is related to energy. Think of it as like potential energy. So we've already looked at things that have potential energy. Our batteries have electric potential energy. And when those batteries are connected to our circuits, those batteries provide the potential energy that's transformed into electrical energy and then used by our light bulb or whatever other device we have hooked up to that circuit and convert it into some other form of energy. So you can think of this potential difference as things that either add energy to our circuit or things that use energy from our circuit. So this battery is going to increase, it's going to have a positive potential. It's going to increase the potential in our circuit, and then the light bulb is going to use that potential. So the potential difference, if we measured it across the battery and across the light bulb, we would have the same change in electric potential. We would have the same change in energy. Then finally, we have our resistance. So anything that uses electric energy it has resistance. So for now, our light bulbs have electric resistance. The symbol for resistance is just R, but we do have some kind of weird units for electrical resistance. Those are called ohms, and the symbol for that is the Greek letter omega. It's like a little horseshoe looking thing. So if you see a horseshoe shape after a number, then that is a measurement of resistance in ohms. So if we take all of these things and look at them in our actual circuit diagram, so we've talked about the current. So what thing in this diagram represents the current? Well, that would be these arrows that are going around that loop, starting at the positive terminal of the cell or the battery and going around through the resistor and then back to the negative terminal. And since current is measured in amperes, we use what's called an ammeter to measure current. Now, with that ammeter, you do have to connect it within the same loop. The current actually has to flow through the meter in order to measure how much current there is. The resistor is that jagged line up at the top. And then to measure the voltage difference, we would use a voltmeter. That should be easy to remember. A voltmeter measures volts. And we would connect the ends of the meter, one to the one end of the resistor and the other to the other end of the resistor to see what the change in potential, the potential difference is across that resistor. We could also do the same thing to our cell. We would put one at one end and another at the other end. We wouldn't have to have like a voltage flow through. Voltage is just like a charge difference at two different points in a circuit. All right, so back to that initial question. Why would a light bulb be brighter or be dimmer now that we've learned about current, voltage, and resistance? So think about what would happen in a circuit to make the light bulb brighter and what would happen to make it dimmer. So you might be thinking, hopefully you're thinking that the current would have to change. More current is going to mean more intensity for our light bulb in general right now anyway. You would have to take some higher levels of physics before you would deal with a high current meaning a low brightness. We'll just deal with simple circuits in here in regular physics. So let's look at how different materials will actually affect how the current flows through our wires. So we have two general types of materials, things that do conduct electricity, called electrical conductors. The charges, the electrons, move through there easily. Usually you have free electrons in electrical conductors, so those might be things, if you've taken chemistry, you know that metallic bonds are made because you have these positive ions and then you have the free electrons around them. And you might have heard like the term the electron sea or electron glue to hold metal atoms together. Well, those pieces of electron glue, that electron sea is free to move from one ion to the next ion. So that allows metals to be good conductors for electricity. Ionic compounds are also good conductors if we dissolve them in water. You'll see that in your simulation in a minute. But then other materials do not allow electricity to flow easily. So electric insulators prevent electricity from flowing. So most molecular compounds are actually good electric insulators. And you might be thinking, wait a second, I thought water was able to conduct electricity, right? That's why you don't want to be in a pool during a lightning strike. Well, that water usually has other things like ions dissolved in it. Those are the things that will actually help water conduct electricity. If you had pure water, just pure H2O, it wouldn't be able to, electricity wouldn't be able to flow through. So we also have properties based on specific, like of our conductors, based on how those atoms are arranged. So even if we have a piece of metal, for example, that metal might be a conductive material, but its shape also determines how much resistance it has to that current flowing through it. It might not be a superconductor. It might not allow things, all the electricity to flow through crazy easily. It might slow it down just a little. So resistance, slowing down of that electric charge, depends on what material you have. For example, like copper and iron have different amounts of resistance. They have different resistivity. And then the shape will also provide more or less resistance. So you can kind of think of this, remember those electrons are like jumping from atom to atom in our circuit. So if you have, it's kind of like cars driving on a highway. If you have a wide highway of all these spaces that the electrons can move through, so if you have a thicker wire, it's going to be easier for electricity to flow. Think about like the power lines. Like most power lines are much thicker than the wiring in your house, for example. And that's because that would have a lower resistance. Then shorter wires, I mean, the like less distance you have to travel to get from one end of your battery to another, for example, the lower your resistance is going to be. So longer wires have higher resistance and thinner wires have higher resistance, but thicker wires and shorter wires have less resistance. So keeping all of that in mind, you are going to, oh, I forgot one little thing. So the other thing that also does affect resistance that you don't necessarily have to know in this course, but it is kind of, it's relevant for if you do some labs with this or if you're using this in your everyday life. Hotter wires also have more resistance. Think about like when materials get hotter, the atoms move faster. So those atoms moving around get in the way of the electrons that are moving through. That's the simplest way to put it. All right, so now you are going to complete this conductor and insulator interactive. So there's a simulation. It's the next thing on your Canvas module. You are going to open the simulation and basically go through each of these materials, put them in your circuit here, and figure out, well, which ones do conduct electricity and let the light bulb light, and which ones don't conduct electricity, which ones don't work, and then submit that on Canvas. And once you've done, hopefully you already did that circuit inquiry activity, but once you've done that and this conductor insulator interactive, then you're going to take the first circuit quiz, the circuit basics quiz, and you can use any notes you've taken and you can use your lab sheets as well. All right, so good luck. Let me know if you have questions.